It came from beyond our solar system, a silent traveler, born among stars we have never seen, carrying with it the chemical whispers of worlds that orbit alien suns. For months, it vanished behind the glare of our own star, lost in the blinding brilliance of the solar corona. And now, against all astronomical odds, it has returned. But something has changed. It shines brighter, it pulses, it seems almost alive. This is no ordinary comet. This is our third known interstellar visitor, designated 3I, also known as Atlas, and its comeback is rewriting the script of cosmic exploration. When the first faint streaks of light reappeared on astronomers' detectors, they could hardly believe what they saw. The brightness curve didn't fit any model. The emissions didn't behave like those of a normal comet. The object, once dim and retreating into the sun's shadow, had re-emerged glowing with an intensity that defied its distance. What could cause such a transformation? Could the heat of the sun have triggered a volatile eruption beneath its crust, or was there something else, something deeper and stranger, at play? For centuries, humanity has gazed at comets with a mixture of awe and fear. Once they were seen as omens, now we know them as frozen relics from the dawn of planetary systems. But this one, this luminous wanderer, carries a secret far more profound. It does not belong here. Its speed, its trajectory, its peculiar orbital tilt all tell the same story. It came from the great interstellar void, crossing the dark gulfs between stars, and just by cosmic coincidence, it has brushed through our neighborhood once again. Imagine that. A messenger from another star system, passing through the invisible borders of our own. It's as if a bottle thrown into an infinite cosmic ocean had drifted across light years to wash up at the edge of our planetary shore. Each grain of dust within it may hold the molecular fingerprint of a completely different solar nursery. Clues to how other worlds, other comets, other forms of matter were forged in distant stellar forges billions of years ago. And now, in a twist no one predicted, the spacecraft Hera and Europa Clipper, each with its own separate, carefully calculated mission, are on trajectories that will take them through the faint, ghostly wake of this interstellar comet's tail. Two robotic explorers, built for entirely different purposes, will soon fly through the breath of a cosmic visitor that was never meant to cross their path. The odds are staggering, almost beyond belief, yet the timing is perfect down to the day. Scientists describe it as pure, astonishing astronomical luck. Both missions are already on their respective journeys. Hera heading toward the twin asteroids Didymos and Dimorphos to study the after effects of NASA's DART impact test, and Europa Clipper on its way to the icy moon of Jupiter to search for signs of habitability beneath its frozen shell. Neither mission was designed for this, and yet, like two travelers meeting at a crossroads they never intended to find, both will pass within a cosmic breath of the glowing plasma tail of 3I Atlas. The comet's ion tail now stretches for millions of kilometers, a ribbon of charged gas and water vapor streaming away from the sun like a celestial banner caught in the solar wind. Somewhere in that luminous mist, countless charged particles drift and dance, each carrying within it a trace of the alien system from which this visitor once departed. Soon, Hera and Europa Clipper will glide through this otherworldly veil, and their instruments, or at least those of Clipper, will listen to its electric song. But before the data, before the science, there is the wonder, the realization that in the endless, indifferent expanse of space, timing and trajectory have converged to offer us a moment of connection, a bridge between two stellar neighborhoods, fleeting yet profound. What will we find in this alien dust? What stories might it tell about the worlds beyond our sun? Could it whisper something about how life begins or how it travels? For now, the answers remain wrapped in mystery, glimmering faintly in that bright, pulsing core beyond the orbit of Mars. Humanity waits once again on the edge of discovery. gazing into the cold dark, ready to listen to what an interstellar wanderer has to say. In the quiet precision of modern astronomy, surprises are rare. Every orbit, every particle, every reflection of light is charted, modeled, simulated thousands of times. Yet even in this age of data and prediction, the cosmos has its own sense of drama. And few events embody that truth as powerfully as the return of the interstellar comet now known as 3I Atlas. What began as a faint, distant detection has turned into one of the most captivating astronomical stories of the decade, as scientists worldwide race to understand why this visitor from another star now glows with an intensity far beyond what anyone anticipated. The first confirmed observation of 3I Atlas came earlier this year when the Atlas Survey System, the Asteroid Terrestrial Impact Last Alert System, noticed a strange, fast-moving object whose velocity and trajectory could not be explained by ordinary solar system dynamics. From the beginning, its hyperbolic orbit revealed its origin beyond our Sun's domain. Like its predecessors, Oumuamua and 2I Borisov, it was a true interstellar traveler. Yet, from the very first measurements, something about Atlas seemed different. Its nucleus was volatile, its outgassing erratic, its brightness curve inconsistent with known cometary behavior. Astronomers quickly realized that this was not a quiet, dormant body passing through. It was a restless, active visitor, shedding its outer layers with remarkable energy. As the comet neared its perihelion, its closest approach to the Sun, on the 29th of October, telescopes around the world watched in astonishment as it flared brighter, its ion tail stretching millions of kilometers into space. But this was no simple reflection of sunlight. Spectrographic readings showed an unusual composition, strong emissions from ionized water and cyanide radicals, but also strange transient lines that could not be easily matched to common molecular species. The object was alive with reactions, glowing in a rhythm that seemed almost to pulse, as if the comet itself were breathing in the solar wind. To make the event even more extraordinary, two spacecraft, Hera and Europa Clipper, found themselves on intersecting trajectories with the comet's extended ion tail. This was not planned. It was not coordinated. It was quite literally a cosmic coincidence. Hera, operated by the European Space Agency, is on its way to study the asteroid pair Didymos and Dimorphos, following the DART impact experiment that altered Dimorphos's orbit in 2022. Meanwhile, NASA's Europa Clipper is en route to the Jovian system, its mission to investigate whether the icy moon Europa could harbor the conditions for life beneath its frozen crust. And yet, by sheer serendipity, the paths of both spacecraft cross the diffuse wake of 3I Atlas at just the right moment. Hera is expected to pass through the region between the 25th of October and the 1st of November, while Europa Clipper will glide through a similar stretch between the 30th of October and the 6th of November. According to models produced by a new simulation platform named Tailcatcher, both spacecraft will come within roughly 8 million kilometers of the comet's ion tail, close enough to encounter drifting particles and ionized gas. That distance may seem enormous by earthly standards, but in the scale of cosmic observation, it is tantalizingly near. No human-made probe has ever approached a verified interstellar object before. Even if the spacecraft do not pass through dense cometary material, they will traverse the outskirts of its plasma field, an invisible current of charged particles shaped by the solar wind and the comet's own volatile emissions. Scientists are calling it a once-in-a-lifetime opportunity to sample the interstellar medium, not from afar, but through direct interaction with material that originated around another star. Of the two spacecraft, Europa Clipper is best equipped for this encounter. Designed to study the electromagnetic environment of Jupiter and its moons, Clipper carries high-sensitivity plasma detectors, a magnetometer, and instruments capable of measuring charged particle densities and energy spectra. These sensors, though built for an entirely different mission, are perfectly suited to detect the subtle signatures of the comet's tail: fluctuations in ion density, changes in magnetic field orientation, or variations in electron temperature caused by interaction with the solar wind. Should Clipper detect even a faint anomaly, it would provide the first direct data from a comet not born in our solar family. Hera, by contrast, is less fortunate. Its instrumentation focuses on imaging and gravitational measurements related to asteroid impact analysis. It lacks a magnetometer or plasma sensor, meaning that while it will pass through the same region, it will not be able to record the comet's electromagnetic characteristics. Still, Hera's exact trajectory data will help scientists refine the geometry of the event, constraining the models of where the tail's plasma and dust streams actually lie. In this sense, even its absence of measurement becomes a valuable calibration point, a silent witness to a cosmic crossing. The excitement surrounding this event extends far beyond the agencies involved. Research centers across Europe, the United States, and Asia have already prepared observational campaigns to support the spacecraft data with telescope monitoring from Earth. Spectral analysis from observatories in Hawaii, Chile, and the Canary Islands will track the evolving brightness of Atlas, measuring how its activity changes as it moves away from the Sun. At the same time, heliophysicists are modeling how variations in the solar wind, the stream of charged particles emitted by the Sun, may distort or push the comet's ion tail. Because these conditions can change within hours, predicting the exact structure of the tail during the spacecraft flybys is a monumental challenge. This is where the tailcatcher model becomes critical. Developed as a joint European-American software initiative, it simulates the dynamic interactions between cometary ions and the solar wind's magnetic field. By feeding it with real-time solar data, scientists can estimate where the densest part of the tail might be, allowing them to interpret the spacecraft data once it arrives. But as with all models, there is uncertainty. And in space, uncertainty is part of the adventure. Why does all this matter? Because every interstellar object is a messenger from another cradle of planets. Each grain of dust within 3I Atlas is older than our solar system itself, forged in the protoplanetary disk of a star that may no longer exist. Its chemistry holds the memory of alien worlds, perhaps even the building blocks of life formed under different cosmic conditions. When scientists analyze the composition of interstellar comets, they are not merely studying ice and dust. They are looking back in time, peering into the laboratories of creation scattered across the Milky Way. Until now, our knowledge of such visitors has been indirect. We observed Oumuamua only as it sped past, too quickly for any probe to reach. We studied 2I Borisov through telescopes, detecting its hyperactive gas emissions but never sampling its material directly. 3I Atlas, however, presents something entirely new, a chance to sense an interstellar object from within its environment. The spacecraft that will pass through its tail are not chasing it. They are already there, moving along trajectories set years before anyone knew of this visitor's existence. It is as though the universe itself arranged the meeting, placing our robotic emissaries exactly where they needed to be. The potential outcomes range from subtle to revolutionary. If Europa Clipper detects even trace amounts of interstellar plasma or magnetic anomalies, scientists could compare them to those found in comets native to our solar system. Are the ions emitted by Atlas similar in energy and distribution to those of local comets, or do they carry unique signatures that betray their origin? Do its charged dust particles respond to the solar magnetic field in familiar ways, or does their motion reveal different physical properties, perhaps a clue to their birth environment? Each of these questions opens new windows into comparative planetology, stellar chemistry, and the evolution of cosmic dust. Even a non-detection would carry immense value. If Clipper records nothing unusual, it would place strict limits on the density and composition of interstellar comet tails, refining our theoretical models for how such bodies interact with the solar wind. In this way, absence becomes data. Silence becomes knowledge. But if the spacecraft's instruments do pick up signals, faint variations in magnetic flux, localized changes in ion density, traces of rare molecules, the implications could be staggering. Scientists would be holding, for the first time in history, direct evidence from a body formed beyond our Sun. These readings could tell us whether interstellar comets share a common chemistry with our own, or whether they are fundamentally different, the products of alien star systems with unique conditions. Such discoveries could reshape our understanding of how matter circulates through the galaxy, how the dust of one world becomes the seed of another. At research centers around the globe, anticipation runs high. Teams at NASA's Jet Propulsion Laboratory and ESA's European Space Operations Center are synchronizing data timelines, ensuring that the brief window of opportunity, just a few days at most, will not be wasted. Because the solar wind changes so rapidly, even small shifts in timing could mean the difference between crossing a dense part of the tail or passing through empty space. The spacecraft cannot alter their trajectories significantly, but they can adjust their sensors, fine-tuning orientations, and sampling rates to maximize their chances of detecting the faintest whisper of interstellar matter. For scientists, this encounter is more than an experiment. It is a glimpse of cosmic luck at its finest. Two missions, conceived for entirely separate purposes, now collaborating in an unplanned ballet around the Sun, intersecting with a visitor from another world. There is poetry in that alignment, the kind of serendipity that reminds us why space exploration still carries the power to astonish. Soon, data will begin to flow. Numbers, waveforms, spectral lines. The language of the cosmos will once again speak in its quiet, intricate way. Within that data may lie the first clues to what comets are like in other star systems, how they evolve, how they survive their journeys through interstellar space, and how they interact with the fierce breath of alien suns. Humanity stands on the threshold of hearing that story, told not by light years of separation, but through direct contact, however fleeting, with material that has crossed the gulf between stars. This is what makes 3I Atlas more than just another comet. It is a bridge, a cosmic handshake between distant origins. And through the collaboration of Hera, Europa Clipper, and the patient vigilance of scientists across the world, we are about to glimpse, for the first time, the living chemistry of another solar system mingling with our own. Long before it became a glowing enigma in our skies, 3I Atlas was already on an unimaginable journey. Somewhere far beyond the faintest reach of our telescopes, it was born in the cold outskirts of a different solar system, a region where ice and dust gathered around a young, forming star. Over billions of years, gravitational tides from passing giants or nearby stars might have nudged it free, sending it adrift into the interstellar void. There, it wandered through darkness older than human history, moving in silence through the deep galactic night, carrying within its frozen heart the unspoken memory of another world. When it finally entered our Sun's gravitational domain, it became, for a brief cosmic moment, part of our story. Now, as it glows once again near the Sun, its bright tail unfurled like a cosmic banner, scientists stand at the edge of an unprecedented discovery. Every detail of this object's journey tells us something about resilience, time, and the way matter travels between stars. For all our instruments, all our missions, it still feels humbling to remember that this icy traveler spent millions of years crossing an ocean of emptiness, only to appear precisely when our species was advanced enough to notice it, and even send robotic emissaries to meet it. There is a quiet poetry in that timing, a whisper that the universe, vast and indifferent though it may be, occasionally allows for moments of synchronicity. To understand the importance of this event, one must also appreciate the machines now tracing its ethereal wake. Hera and Europa Clipper are not mere spacecraft. They are the culmination of decades of human craftsmanship, engineering, and persistence. Hera's story began as part of a bold effort to test a planetary defense concept, the idea that humanity could alter the orbit of an asteroid. When NASA's DART mission slammed into Dimorphos, changing its trajectory ever so slightly, it proved that intelligent life could, in principle, reshape celestial motion. Hera was designed as the follow-up, to measure the aftermath, to quantify the subtle gravitational consequences of that impact. But destiny had another task waiting. By cosmic coincidence, Hera's path through the inner solar system placed it within reach of a visitor from another star. It will pass quietly, perhaps without the right instruments to measure the glow of plasma or magnetic waves, but its presence will mark humanity's first attempt, however accidental, to reach across interstellar boundaries. Europa Clipper, on the other hand, represents our enduring fascination with life beyond Earth. Its instruments were built to probe the subsurface ocean of Europa, where liquid water lies beneath kilometers of ice, warmed by tidal forces and hidden energy. It carries plasma sensors, magnetometers, and spectrometers capable of reading the faintest whispers of charged particles, tools meant to study a moon, yet now repurposed by fate to touch an interstellar phenomenon. In a sense, Europa Clipper becomes the perfect ambassador for this moment, a mission about the search for life, encountering material that may have formed in a completely different cradle of existence. Both missions remind us of the unplanned beauty of exploration. Science, for all its equations and control, is still driven by chance, by the convergence of timing, geometry, and curiosity. When the data from these spacecraft arrive, whether they show rich traces of alien ions or the quiet silence of emptiness, they will be woven into a broader human narrative. Because every measurement, even the smallest, carries the echo of a question older than civilization. How many worlds are there like ours? And what connects us all across the distances between stars? The comet itself, 3I Atlas, will continue on its way, its trajectory curving out of the solar system once more, bound for another epoch of solitude. Its newfound brightness may fade as it retreats, the heat of the sun no longer stirring its volatile ices. But the light it reflected, the tale it unfurled, and the energy it released will linger in the records of observatories and the memories of those who studied it. Long after it vanishes into the blackness, we will still be deciphering the messages contained in its spectral fingerprints, comparing its chemistry with the dust of Borisov, the enigmatic shape of Oumuamua, and the countless native comets that orbit our sun. Perhaps the most enduring legacy of this event will not be the data itself, but the shift in perspective it brings. For the first time, humanity is not merely watching a cosmic visitor pass by. We are participating in its passage. We are there, through our machines, through our intellect, touching the edge of another stellar system's debris. And through that contact, however faint, we are learning that the boundaries between stars are not barriers, but bridges. The same processes that shaped this interstellar comet shaped us. The condensation of gas, the pull of gravity, the quiet alchemy of elements forged in the hearts of ancient stars. Future missions will be built with this in mind. The Comet Interceptor, already planned by the European Space Agency, is designed to lie in wait for a yet undiscovered visitor, ready to launch into pursuit when the next interstellar wanderer approaches. The lessons from 3I Atlas, the calibration of sensors, the refinement of plasma models, the courage to adapt, will inform those missions. They will remind engineers and scientists that sometimes the greatest discoveries happen when you least expect them. When the story of 3I Atlas is told in years to come, it will stand as a symbol of a turning point. The moment when human exploration quietly reached beyond the sun's family and brushed against the unknown. Hera's silent passage, Europa Clipper's careful measurements, and the glowing path of the comet itself form a trinity of discovery. One human, one mechanical, one celestial. Together they compose a narrative that speaks not of separation, but of connection, the continuity of matter and curiosity across the infinite dark. And somewhere out there, beyond the heliopause, beyond the whispering edge of our sun's domain, another comet is waiting. It too may one day cross the thin border between the stars and approach our world. By then, perhaps, we will be ready, not by accident, but by design, to greet it, to listen, to learn. Until that day, the memory of 3I Atlas will remind us that even in the vastness of space, where the silence seems eternal, there are moments when the universe speaks. And if we are patient, if we look carefully enough, we can hear its voice echoing through the data, through the light, through the endless beautiful dark.